In this set of Snap Circuits videos, we're continuing to look at the PC projects from the CI-73 expansion of the SC750 set, starting with the AM Radio PC here, Project PC12, and going up to Project PC20, which is the, let's see, Space War Flicker PC over here on the side of the book. Now we're actually going to skip over the AM Radio PC here because there's pretty much 2 to 3 problems with it that I have, but you probably won't. I've even marked it, I noticed too. Anyway, the problem I have with the AM radio, and this has been covered in previous times I've made the AM radio, is number one, this location here has all kinds of electrical noise and interference in the vicinity of the project here. So if I were to just turn this on, it just makes all kinds of noise. And trust me, I have it tuned to an actual AM radio station, but I have to be in the middle of the room where the least amount of noise is to actually hear it. So when it's around anything else, here we're trying to record, even the camera here for instance, I think there's just too much electrical noise and we end up hearing the whole 60 hertz buzzing through the speaker. The other problem is when it's plugged into the computer, it's probably not going to be as noticeable here to you, but when it's plugged into the computer, we're not even seeing the proper waveform from the AM radio circuit here. We're actually getting the waveform of the electrical noise and the AC charger for the laptop here. So because of that, you can't even get the proper waveform to show on Winscope for this. Again, there's just too much noise in the vicinity to see it. So we're just going to skip over the AM radio project. The way that your waveform should normally look is you should see a nice little kind of sinusoidal waveform on there that changes up and down or widens in and out as people are talking or music is playing over the radio there. But as I say, because of not being able to filter out the noise and stuff like that with the way Snap Circuits is, I can't show you anything on the AM radio, much less even have the circuit work by itself with all the noise here. So we're just skipping over the AM radio PC. So we're going to go on to Project PC13, which is the Space War PC. So here's Project PC13, the Space War PC. There it is in the book, and here it is on the board. So we've got our Space War IC going out to our whistle chip and our 6-volt lamp instead of the 2.5-volt lamp because we have 6-volt power here, so it's safer if we have the 6-volt light there so we don't burn out our 2.5, 3-volt lamp by accident, because that has happened before. And we just turn on our circuit and nothing's going to happen right now until we press our press switch, and that will cycle through the Space War IC. So let me get Cam Studio recording our oscilloscope here. Okay, and get the scope recording. And so as we cycle through the sounds, we will get different waveforms on the oscilloscope, and I've already preset it with the trigger and half millisecond division and all that stuff, so we can see what it does. So this first sound with the bomb drop actually makes a pretty good waveform, because you see when it starts out with a high frequency and then the frequency drops, so we see an increase in the wavelength here, and then when it gets to the explosion part that we can see on the light there, of course the waveform changes when it gets to that point. Let's try another one. So our little machine guns kind of sound effect thing going there. You can see how its waveform is working there. Another one. Let's see how that Space War sound is. Yeah, another gun kind of sound effect on there. We can see the variation in the waveform on this one compared to the previous one. Actually, let me move my mouse pointer out of the way. And you can see this one's at a lower frequency with a different sound, and that's easily being reflected here on the waveform, and it's constant too. And there's another one, but that one's a little higher frequency than the last one. And of course that one's a nice high frequency repeating one as seen on the waveform. And then we're back where we started. So now let's look at that in the FFT, because that will look kind of interesting there. So let me switch over back to that division and look at these with the FFT scale. And you can see how that one has got the peaks going right there. And you can see with that one alternating, that you can see the FFT bouncing back and forth between the two different variations on that, along with our flashing light. Oh, the hand's getting crappy holding this button down so hard. Another FFT waveform of that one. And of course, this one produces a nice peak right here on the FFT. Oh, that little ripples. And when we vary it, we see the FFT changes as well. So it's got a little more coming out to the right here. And our bomb dropping one is interesting because we see those three peaks and then they all come to the left side there. And then there's that little machine gun effect, as we can see on there. Oof, my hand gets crampy holding that button down. So that's basically Project PC13, how its waveforms look. So now we're going to look at Project PC14, which is the microphone. Let's stop this. So now we're looking at Project PC14, the microphone. Here it is in the book, here it is on the board. So basically we're just using our microphone with a 5.1K resistor through a 6-volt source there. So we have it hooked up to our computer, so I'll just power up the circuit, then get Cam Studio started here. And now we got it going. So for this we're using the 5 milliseconds per division scale. And here I'm basically just going to blow into the microphone and we'll see a waveform here on the computer up here. So by blowing on the microphone there and also varying how hard or soft I blow on it, I can manipulate the waveform and the intensity of it. And let's look at this on the FFT scale. Now of course you can do other things with the microphone like talk into it or whistle into it or things like that. I'm just using a straw and blowing some air into it for demonstration here. So again, by looking at it on the FFT scale, we can see on the corner there how we can affect some stuff on it. Of course, you can do some tapping and other stuff on it to make some noise. Basically, you're just generating a signal there that the oscilloscope picks up. But for that, we're going to move on to the next project, which is pretty simple, which is PC15, the speaker microphone. Stop this. So I have Project PC15 here, which is the speaker microphone. And like the AM radio, it seems like I'm not going to be able to show a whole lot on this because we're just using the speaker to show a waveform here. And I'm just going to give you a snapshot of it. There's no point trying to record it because with the gain control even set to maximum here and using a combination of the wake command, this is what the waveform looks like if I just tap on the speaker here with one of these. So I'm either, again, still getting a lot of noise through the computer, or I just can't get the signal amplified high enough here on the laptop without changing a whole bunch of settings, versus, again, what they kind of have in the book here for that. So I'm just going to move on to Project PC16, which is the Symphony of Sounds PC. So here we are looking at Project PC16, the Symphony of Sounds PC. There it is in the book. There it is on our board. So we're using all three ICs, the Music IC, Alarm IC, and Space War IC, and combining all their outputs to the whistle chip, which I'm using in place of the speaker, and also our 6-volt lamp. And then our Space War IC can be controlled via our photoresistor and press switch here to change the various sounds. So let me go ahead and get Camp Studio started. Get our oscilloscope going, and then we turn on our circuit. So we can hear from the whistle chip and see from the pulsation of the light there all the combined signals from the Alarm IC, Space War, and Music ICs there. And based on our waveform, you can see all the signals being combined on our display there, which again is trying to produce something similar to what's in the book here. In fact, we just changed the Space War IC signal by covering the photoresistor there briefly. You can see a little bit of variance on our signal there. Now let's see what our FFT looks like. You can see our FFT changes a little bit there at times. We'll bring our thing down there at a time. So that kind of gives you an illustration of what the signals look like on the oscilloscope when we combine all our ICs together. Get this pause. So now we're going to move on to Project PC17, which is the Doorbell PC. Stop this. And now we're looking at Project PC17, which is the Doorbell PC. There it is in the book, and here it is on the board. So I've modified it a little bit by putting the press switch over here on the hold function of the Music IC, because the replay didn't seem to be working for some reason. So I'll just hold the button down if we need to continue playing the Music IC. Anyway, it goes to our whistle chip and our 2.5 volt, 3 volt lamp with our 3 volt supply. So let me get the oscilloscope going. And we've got it already set up for a 0.5 millisecond division on there with some settings, so when I turn on the circuit, we can see this little sort of sawtooth type of waveform there. This thing goes away, and then of course I can bring it back just by holding down a press switch to keep it going. Now let's see what that looks like on our FFT. Switch the scales around. Try it again now. And you can see on our FFT scale there how, of course, we got the peaks kind of descending toward the right as it's playing. And it does fluctuate a little bit as the notes play from the Music IC there. So that is how project number PC17 works. Let me stop. Now here we are with project PC18, the Periodic Sounds PC. There it is in the book, and here it is on our board. So we have our alarm IC, and that output is both driving our 2.5 3-volt lamp, but also it's driving our music IC, which is then going through our R1 resistor and then through the speaker. So let me get Cam Studio recording our oscilloscope and get it online, and I've got it configured with the time delay and the proper gain. So we turn this on. We get a waveform here that you see is kind of alternating between a couple of peaks that go to rest and then the high frequency sound of the music IC. So again, we're seeing the signals of the alarm IC and music IC kind of being interleaved, switching between each other. So the signal here that's got the spacing between it with a couple peaks is of course the alarm IC, and then the music IC is the one that has the constant peaks here going up and down. And because the alarm IC is also driving the music IC, it's periodically interrupting the music IC's playback. Now let's see what this looks like in the FFT scale. And again, you can sort of see it too, where it's periodically going between being all up on the left side here, and then coming into these individual peaks that kind of go lower and lower as they come out further. So that's how Project PC18 works. So we're looking at Project PC19, the lasting doorbell PC. There it is in the book and on the board here. Now I've taken the speaker out and replaced it with our 2.5 3-volt lamp there so that the circuit is not as loud, because we'll still get the output from our whistle chip. So let me get the oscilloscope started. So we've got a little Darlington transistor style oscillator circuit here, which is being held by our 100 microfarad capacitor there. Let's start the playback of this. And the circuit's already turned on, so it'll let me power up the circuit. So as long as I'm holding down the press switch, it's keeping the capacitor charged and keeping our oscillating circuit going. We can hear the tone from our whistle chip and see our 2.5 3-volt lamp glow a little bit, and we of course can see the waveform on the oscilloscope. Now when I release the press switch, the frequency starts getting lower and lower, because as you look on that oscilloscope, the waveforms the peaks are getting further and further apart, and of course the frequency is dropping. Until it completely goes out. Let's see if we can adjust our time delay a little bit here. So that gives us a little better view of the peaks now. And as you saw earlier, as the frequency goes down, the peaks just move more and more to the right, as the circuit oscillates slower and slower, until the capacitor completely runs out of power and the circuit goes dead. Like that. So now let's look at this on the FFT scale. Bring T back down. So when we look at our FFT, everything looks pretty normal there. But with the FFT scale, as we see, not only do we see the frequency changing, but we can also see the amplitude of the peaks there going down, because the FFT is frequency over time versus the scale we were looking at. So that's how Project PC19 works. Stop the oscilloscope. Here, Project PC20, the Space War Flicker PC. There it is in the book, and here it is on the board. So with this, we have our alarm IC driving our Space War IC, and that's making it cycle through different outputs and that we see reflected on our red LED. So let's bring up the oscilloscope here. And I've already got it configured somewhat. Get online. And we turn on our circuit. We see that our red LED is changing multiple states from kind of being constant to flickering to flashing and a couple of different things. Again, as the alarm IC switching on and off makes the Space War IC change the output on it, because it's again got 6 or 7 different Space War IC sounds in there. And we're seeing that reflected on our waveform here as the different signals from the Space War IC are being picked up on our oscilloscope there. And again, we see it visually through our red LED as well. Now we can't hear anything, of course, because we don't have anything like a whistle chip or speaker or motor or anything like that that can, of course, make us hear the signal. So we can only visually see it here. So let's change to the FFT, and when we change over to the FFT, you can see that even the FFT scale is varying quite a bit. Again, as the Space War IC is cycling through different outputs. Again, as the alarm IC drives it. Okay. And of course, that's what the signal kind of looks like when we take out the divisions. So that pretty much concludes this set of Snap Circuits.